Good morning. My name is Gerald Persaud, and I'm the VP of Business Development for Reflex Photonics. Reflex Photonics is a manufacturer of rugged optical modules, and we are based in Montreal, Canada. Today, what I'd like to talk about is scalability and interconnect technologies. And the first question you might ask is, well, what is scalability? So scalability to me really is the ability of a system to add more capability with relative ease. The second question is, why is this important? And why it's important is we see technology changing at a faster and faster pace and making systems just as obsolete at that same speed. So really, we have to try to figure out how to make these systems keep up with the change in technologies. To illustrate this, here's just a picture I took off of the internet, but it's an Airbus commercial aircraft showing the extent of the wiring and the complexity of that wiring. And why that picture should show very clearly why scalability is important. It would be a very daunting task to have to change that wiring within a system if you decide to upgrade it. So for example, if that was not fully thought out right in the beginning, the life of that equipment may be cut short because it really cannot be upgraded. Some of the things we look at in terms of the scalability or design considerations would be, I look at as change complexity. On the right-hand side of the slide here, basically what you've got is a typical system there where there's a number of sensor systems, so things like a radar, infrared cameras, and that would be interconnected with Ethernet switches. You'd also have a command and control panel with displays and control systems, storage, and servers. All these are modules or systems or components that make up that system. And again, what I would look at is how difficult would it be to change those systems in order to upgrade the overall system. Interconnect, as I shown on the previous slide, is a very difficult thing to change. So that would have very high difficulty. Computing, on the other hand, if you've architected, say, a VPX type computing architecture where you can change out board, then you can potentially open up the box and put in your latest advanced processor and increase your processing scalability. Life cost is another thing that we want to consider. So for example, if you're looking at equipment that has a 40-year life, and you make the system very tightly integrated, then that may be very difficult to upgrade in later years. And again, you may end up shortening the life of that equipment because the cost becomes unsustainable from what it was initially planned for. Infrastructure sizing is a key parameter of scalability. We look at things like interconnect bandwidth. So for example, if you put in a copper interconnect versus fiber, where fiber can potentially scale to hundreds of gigabits per second, whereas copper may just limit you to a gigabit per second, then what you would end up with is having to rip out all that infrastructure, which would be very costly, and oftentimes you can make an equipment obsolete in terms of that process. Cooling is something else that we have to look at as we put the system together. Power and distribution, of course, we've got to size the power correctly, and we've got to have a distribution architecture to be able to add new components to that system as we try to scale it. Open standards, that's something the whole VIDA community is very concerned about, and there's many open standards that are being introduced, such as HOST and SOSA and FACE. But really what you're trying to achieve with the open standard is a lower cost of the equipment to allow mixes of hardware and software components to rapidly scale. You're also looking at how quickly can you install these different capabilities. I look here in the next component here is modular versus integrated. And although not every subsystem needs to be modular, some systems can be tightly integrated because making a modular architecture, it does have a certain overhead attached to it. And if you if you take modular too far, you can end up increasing the cost of the system or make it almost impractical. So these are some of the trade-offs that has to be considered. Now, the last thing that really what I'm looking at here is fast technologies, and that's what I am really concerned about because that's where I see scalability has to be very effective. And there are many fast technologies that are coming on board. What we don't want is to have attempt to install a fast technology, but by the time we're able to modify the system infrastructure to support that, the technology is already obsolete. And as I showed you in the very first slide, that can easily happen if you decide to change the interconnect infrastructure. By the time you change that infrastructure to, say, implement a new artificial intelligence system, you might find that it's obsolete, or so you can't really keep up, and the equipment is no longer viable. On the next slide, I'm looking at some of the fast technologies that I see, and these fast technologies I consider very disruptive because they can really give the competitors an uneven advantage when they are deployed. So deep neural networks is something that we've been hearing a lot about in the last 10 years. A tremendous amount of investment is going into this in the commercial sector. We hear of big data all the time. We hear of IoT. We know Facebook, Google, Amazon, all these people are investing in this technology because of the value it can provide. You look at everything is smart these days, so we look at smart cars, smart city. And this technology is real. It has the potential to truly disrupt the way things are being done. So it's very important that we keep an eye on it and understand how do we make our systems such that they can adapt to this very quickly. Augmented and virtual reality, we see adding a lot of capabilities towards things like pilots, delivering a rich set of data to a pilot to allow them to make accurate, informed decisions, and even aiding them in the operation of the equipment. Unmanned vehicles, we see rely on virtual reality to be most effective in terms of piloting something that's remote. Graphics processors is really the key technology that's driving a lot of these fast technologies. We saw graphics processors that only a few years ago that might have had a couple hundred cores in them. NVIDIA's latest processors can have up to 6,000 cores in them. So we're seeing a tremendous amount of processing capability almost increasing at an exponential pace, and that's what's really powering smarter technologies or augmented reality or virtual reality. Solid-state memory, that's another key component in terms of localizing information storage. We're seeing terabits of data now moving into just a few small chips. So there's a lot of knowledge in smaller chips, making these systems more and more autonomous. High-res sensors, things like cameras and radar. Basically, we just want to get more accurate information, so these things are becoming it's just trying to get more information or more accuracy in terms of what we see. And finally, high-resolution displays, which we're all trying to get a better picture of what we're looking at so that we can make more effective decisions. Now, tying all of these technologies together, what we see is optical transceivers, which is the basis of the interconnect with it. And at Reflex, what we try to do is deliver unencumbered bandwidth to make all these systems work seamlessly together. So we really see optical interconnects as a bridge to hooking all these technologies together. So what I want to talk about for the remainder of the slide is more about optical interconnects because, again, we see that as really the bridge to all the fast technologies. In optical interconnects, you really have a choice of two main types of technology, which would be multimode transmission or single-mode transmission. Multimode transmission is typically for applications requiring less than 300 meters of reach, whereas single mode is for 2 kilometers and beyond. They can go into the hundreds of kilometers. Single mode tends to be applied more in the telecom industry. It's generally a more expensive architecture. It's more difficult to work with, and it has some sensitivities to harsh environments. So we typically do not recommend a single mode for very harsh equipment. It does have the ability to deliver massive amounts of bandwidth with things like what they call dense wave division multiplexing. But really where we see multimode, on the other hand, can give you very harsh transceivers that you can work over wide operating ranges with no external thermal conditioning of those transceivers. As well, they're lower in cost, they're smaller, and less in power. So really the choice for us in terms of looking at mobile type of equipment working in a harsh environment is really multimode type transceivers. So this whole discussion that I'm having right now is really about scalability. And on this slide, what I'm showing really is how we see rugged embedded optical modules scaling. So today we can offer about 300 gigabits per second of bandwidth in a small chip size device. So the picture in the middle of the slide there shows you what those devices look like. We can do that over about 24 fibers, where we're doing about 12.5 gigabits per second per fiber. We will scale that chip up from 300 gigabits per second today, and we expect to take it up to about 4.8 terabits in less than 10 years. That technology does exist for us to even do today. The main issues with having that much bandwidth is power. So for example, at 300 gigabits per second, we would probably be running a transceiver that's just about maybe 2.5 watts to, between 2.5 to 3 watts. But if I linearly scale that up at 4.8 terabits, we'd be closer to 50 watts. And that's not really practical for a transceiver going forward. So what we're doing right now is investing in technologies to be able to scale the bandwidth while at the same time keeping the power down. So some of the technologies we're looking at would be things like different modulation techniques we call pulse amplitude modulation. And we're also looking at other technologies which would be things like shortwave division multiplexing. It's not quite the same as what the single mode telecom guys use. It uses multimode fiber, but allows you to put more information on the fiber. Also, silicon photonics is another big growth area that basically will integrate the components better, keep the power down, and keep the size down as well. So Reflex is investing in a lot of these technologies to be able to scale into the future and support all these fast technologies that I mentioned before, like artificial intelligence and NVIDIA graphics type processors. On this slide, what I'm showing here is the range of products that could be available when you're implementing your system. So what we've seen over the last few years, or since we've been working with the defense community for, let's say, the last 10 years or so, is we see every application is very unique. It has its own unique set of constraints in terms of the type of interfaces it's looking for, the sizes, the performance, different storage temperatures. And because of that, we've had to construct a wide range of products to be able to support these applications. One of the products that we're really looking at right now that I find is very exciting, and that just increases the I/O density and the bandwidth scalability. On the far right of this slide, you'll see something called the Light Connects combo as an example, and that is something, it has 10 RF contacts in there with an MT fiber that can have up to 24 fibers in there. So that's not only gives you a lot of density in a combination, all of that is done in a half-width VPX type connector. So it's producing a hybrid of RF and optics together, and it's barely about 14 millimeter wide. So that's given an awful lot of capabilities. That just shows you how we're advancing the technology for transceivers. On the next slide here is just showing you some of the applications that are actually taking advantage of fiber optic connects and the transceivers that are built into them. Digital radar is a big application space. Digital radar, essentially what you're doing is they're digitizing the signal right at the antenna panel. So all the processing of the radar is done digitally. That provides many, far more capabilities than what was done in the old phased array type radar. These panels are getting very large, and we have seen a lot of uptake in demand for a transceiver to support these systems. High-resolution cameras, again, another area where we see a lot of fiber optic use, simply because the resolution, the amount of information coming off of that cannot really be supported with copper. So one of the examples that I mentioned is that camera there is called the Argus sensor. It was done by BAE Systems. And there's actually a YouTube video showing the capability of that system. So it's using the fiber optic transceivers to move this massive amount of information. Optical switches is the heart really of systems going forward. We're seeing fiber optic interfaces going in there and connecting everything within the system. High-performance computers, this group is well familiar with that, with VPX and fiber optics being introduced on the host cards now to either go board to board or go outside the box. We've got media converters and a number of other modules. Okay. So just the takeaways from this discussion is fast technologies are clearly creating an uneven advantage. There's a huge race to dominate AI. We see that in most nations who has made it a priority to be a leader in this space. China, Russia has made this a clear priority that they want to be at the head of this game. We know that systems must scale faster than ever to stay viable. And tying this all together is we see optical interconnects as the most scalable technology for fast upgrades and small swap. And that's the end of my presentation. If you have any questions, I will take them now, or you can connect with me later.